Alright, hello and welcome to Lab 1. This is a 2-week lab, so I'm going to take a little bit of time to go over it because I won't have a lab introduction video next week, so technically I'm allowed to, right? So let's get started. This is the lab write-up. It's about SAT solving, and SAT is a new topic. It stands for satisfiability solving. Okay, so what does it mean for something to be satisfiable? We've been talking about these Boolean expressions, these propositions, and you can write as many as you want. There's an infinite number, but they always have some variables and some logical operations. So if we have one of these, a common question that we like to ask in computer science for several different reasons, automated program correctness checking, program analysis, even in your compiler it does this. It's really cool. It checks if these things are satisfiable, okay? To see like, okay, I don't need to compile this part if it's never going to run, things like that. So yeah, a Boolean expression is called satisfiable if there is some value that you can give to these p's, q's, and r's, all the variables. They have to be true or false, one of the two. If there is some combination of true and false that you can give to these variables and make the whole thing true, then the formula is called satisfiable. And we like to find all the different solutions to these formulas. How many different ways are there to make these satisfiable? So for example, this is satisfiable because there is at least one way to make it satisfiable. To set these variables, like p can be true, and q can also be true, and then r, doesn't really matter what r is at this point because it's an or, but we can set r to like true as well. And this is one satisfying solution, okay? A satisfying solution. Okay, so that's satisfiability, and we're going to implement that. We're going to implement this kind of checking. We're going to make Boolean expressions in code. We're going to make classes for those, and we're going to make a function that finds all the satisfying solutions to a given Boolean expression. Okay, that is where we're headed. And so to get us there, let's review some 41 stuff. It's possible that you didn't learn this, in which case I'm going to give you a crash course, and don't worry, it's not a huge deal anyway if you didn't learn this, but inheritance I'm going to require you to know because we're going to make good use of that in this lab. So a smart pointer is really nice. It is the best thing in the world because it is a class in C++ that wraps around a pointer and it calls new and delete for us automatically. It's beautiful. And so all of these smart pointer classes that I'm about to show you, just pretend that, like unique pointer, pretend that it's some fuzzy way of saying t star. That's really all it's doing. Shared pointer, some fuzzy way of saying t star. Because you can use dereference, you can use arrow as you normally would. There's no difference. The only thing is, it's going to call delete for us because it's great. Okay, so yeah, let's start with unique pointers. You can go ahead and look up all this stuff on the memory page. So maybe I should link this here in case you're looking for some documentation. I'll just put this here. So all this stuff lives in the memory header, which is pretty new. It's C++ 11 new, okay? So that's why we use the latest version. Okay, so a unique pointer is just a pointer on the heap that's automatically deleted for you, and it's owned by one person. It is unique, okay? Objects own their pointer uniquely. Nobody else can have access to this place on the heap. Okay, so let me show you an example of unique pointers. So here in code, I have a main function. This is called smartpointers.cpp. I'm going to give this file to you in the code from class in the lab 01 folder. So here is a unique pointer to an int, and you can pretend that it's kind of like int star, okay? Instead of saying new, you say make unique int, and then you give constructor parameters. So when you say make unique, you can give t's constructor parameters right here. Okay, that's what you do. And so I'm going to set the int initially to 42, and when I say star p, it'll print out 42. Smart pointers -o smart pointers, and so I get the 42. Okay, so this is really cool, and I want to prove to you that it's going to call destructors automatically for you once things don't need to be used anymore. So for example, if I say class C, it's very simple. It has an int inside of it. It has a destructor that just says when it's called. If I make a unique pointer, p2, to a C on the heap, what's going to happen is this P2 is going to be automatically deleted for me once we're done with the variable, which is when main is finished, right before it returns. Okay, so P and P2 get deleted automatically for us right before main returns, and we can see the destructor get called there. Okay, so that's happening. One thing you can't do with a unique pointer, because it's supposed to be a unique place, you can't share it to somebody else. You can't say unique pointer P3, or how about I say P2 copy equals P2. You can't do this. Oh gosh, that's ugly how it's formatting that, sorry. How about that? Can't do the above, because the pointer, it's supposed to be unique. So this is going to be a compile time error. It's like, nope, can't do that. You're not allowed to copy things when it's unique. So that's what shared is for. Okay, so a shared pointer, if you want to look that up, it's just a pointer to T on the heap that's meant to be shared among multiple people. You don't have to worry about all this stuff. It can be copied just fine. Instead of saying make unique, you say make shared, and then you give all the constructor parameters for the T again. Okay? And once everybody's finished with that pointer to that thing on the heap, it gets deleted for you, and everything is as normal. So just pretend it's a real pointer. That's all I'm trying to tell you here. So yeah, you can read up about shared pointers if you'd like. Yeah, you can get the star, you can get the arrow, you can actually get the underlying pointer if you really wanted to, but you probably shouldn't. These things can be null still, so you can still segfault, but it's just harder. Okay, it's harder to do things incorrectly here, because it'll always delete it for you. It's much harder to leak memory. All right, so here's just me making shared of some things, like P3 is a pointer to an int, 43. You can print it out with the star again. Get the 43. Can make shared C again. You can copy it around. You can set its X value with the arrow to 44. You can print it out. So it all works. And then the destructor automatically gets called. So I made two C's, one here with a shared pointer, one here with a unique pointer, and they're both getting destructed automatically for me. That is the greatest thing in the world. I hope you agree. Okay, so that's shared pointers. We're going to make use of those in the lab today. Yeah, that's about it. Next thing I want to do is review inheritance. I'm going to give that cat and dog and animal example that everybody likes to give that you probably hate by now. But the idea of inheritance is we have some relationships that we notice in real life, and we want to put those inside of code. And we also notice that if we were to make separate classes and have them do their own thing, we'd be copying a lot of stuff around, and that's useless. We would like to put similar stuff in what's called a base class and potentially override them in subclasses. Okay, so that's the idea. So for example, every cat and dog, well, they have names and they know how to talk. And they have getters and setters for names as well, maybe. With all of that, it's useless to put all this stuff in cat and copy and paste it also in dog. No, that's what inheritance is for. We make an animal class because a cat is an animal, a dog is an animal. That's how you know inheritance is a good idea, when you have this kind of is-a relationship. We can just put the name stuff in animal. We can put the talk method in animal so that we know that every animal has to have one of these. And then we can do special stuff. We can override those methods down here in the subclasses. Okay, I hope this is all coming back to you. Yeah, and if we don't need to override something, we'll just keep it as it is. We can use the name stuff in here because we get it from animal for free. Okay, so shared code. It's beautiful. Inheritance is lovely. So let me go there. That is this example. So here is my main function. I make a shared pointer to a cat. His name is Lonzo. His constructor is for names. Shared pointer to a dog. His name is Cisco because I have a friend who has a dog named that. Why not? And then the cool thing about all this stuff is that you can put them into a vector of pointers to just animals, and all of this stuff works. Like, it knows how to talk properly. It says meow or woof, depending on which thing, right? So let me show you this running, and then I'll talk about how this is implemented. So this should just be a review. Yeah, so it says Lonzo, meow, Cisco, woof. All right. So how does this work? Animal's the base class. It has a constructor which keeps track of setting its name member variable. Every animal has a name, so we might as well put it up here. Okay. And then a talk method. Every animal knows how to talk, but an animal by itself, it's too abstract. So we're just going to make this a pure virtual function and make this animal class, therefore, an abstract class. Hopefully those terms are coming back to you. And then get name, we can have a getter. I won't implement the setter. That just returns back the name. And we can use this down here in the subclasses and not have to worry about rewriting it like it's shared code down here, because we're inheriting from animal in cat and dog. Okay? So to set up, to construct a cat, we can call the animal's constructor to set the name. It's beautiful, using this initializer list. And then for the class-specific stuff, or the subclass-specific stuff, we can override these methods. We can say, okay, yeah, talking for cats, that means we're outputting meow. Okay, talking for dogs, we're going to override this default one. That just means we say woof. Yeah. And so every time we have something, we're asking it to talk, it's a special animal, it'll call the correct one because this is inheritance. It's a virtual method. Okay? That's the beauty of virtual stuff. All right, so yeah, that's the idea. So we can call getName on a cat and a dog because they have those from animal. We don't have to implement them down here. And we can ask them to say things to us. Talk, meow, and woof. Okay, so hopefully now it makes sense why it's doing this. Please study this if you're a bit rusty. Also read that optional reading page. There's good examples in that C++ tutorial as well, I think. But yeah, those are my examples. And now let's look at the real write-up. Okay, so SAT solving, let's do this. Get the code, you'll have this stuff. And what we're going to do is we're going to represent formulas in C++, first of all, and then we're going to find all the satisfiable solutions to a given formula, okay? So we're going to find all of them, all the different ways to make a particular formula satisfiable, all the different, and a solution just is an assignment of variables. So this is one solution. P equals true, Q equals false, R equals false. That's just one, and we want a bunch of them, okay? So let's look at these files to see how we're doing that. Logic.h and testlogic.cpp. So actually, let's start with test logic, because the first test is a useful one. So here I am in test eval. I am building up in code this formula. Okay, this is how I'm doing it. I've got some vars, I've got some nots, I've got an and, I've got an or, and here's how all these classes that I've started for you work, or are supposed to work. We make a variable, call it P, make a variable, call it Q, make a variable, call it R, and now we can use them in our formulas. We need not R, so we can put R inside of a not, okay? We're calling the not constructor. And we can make an and, because we need to make Q and not R, by anding together. This is the constructor call again, Q and not R. That's how we build up this and right here, okay? And then the final operation in this Boolean expression is this or. It ors together P, and it ors on the right side, Q and not R. So we just put in an or, P, and Q and not R. Hopefully that's self-explanatory. And then this is how we store satisfying solutions, okay? This is how we store variables, okay? It's a map. We're going to use maps from variables to Booleans, okay? So this is saying that, okay, whenever you see P, make it false. Whenever you see a Q, make it true, because we're giving that variable. Whenever you see R, pretend that it's false. That's our assignment of variables, okay? And so you're going to help implement this evaluation method on formulas, okay? So given P or Q and not R, we're going to evaluate that using these particular variable assignments, and we should get back true because false or true and not false is in fact true. Okay, and I do the same thing down here for a different one, false, false, and false. In that case, it should be false. Okay, so that is essentially how I want you to think about the code. And so let me show you these classes themselves now, all this stuff. We use inheritance, and it's a bit fancier than cats and dogs now. So here is where it starts. Don't worry about this too much. This is for me to implement a special extract var names method that just goes inside of a formula and gets all the variables that are used. You'll use that yourself. So returns all the variables that exist in the formula. What you're going to be working on is evaluate. Okay, so every formula, oops, sorry, I should put this here to describe it in the base class. So formula is a base class. Everything down here, all the ands, ors, and nots, and vars, they're formulas. Okay, this is the base class for all the logical formulas, and in math we pluralize it as formulae. Yeah, so things that we can do to formulas are evaluate them using a specific assignment of variables to values. So evaluates the formula with a given assignment of variables to values. And so maybe if the var is p, you give true. Maybe if the var is q, you give false. You put all that stuff in a map, and you'll use that when you implement your evaluation method. Okay, extract var names I've made for you. All it does is take a formula, get all the variable names that existed in it. So it gives you back a set of all the variables. And then the destructors, we're just going to keep default. So yeah, that's about it for formulas. And now here's how you build up real things. So an and is a formula, it inherits, and so we implement all the stuff inside of it. The constructor for an and, well, if you're anding two things, you have to take a left-hand side and a right-hand side, okay? So LHS stands for left-hand side, RHS stands for right-hand side, and that's what the constructor takes, yeah? And then extract var names just gets all the variables that are in this particular and operation. We'll talk about evaluate in a second. Similarly, or, if you're oring together two things, you gotta hold the two things, right? You got a left-hand side and a right-hand side again. If you're knotting something, if you're knotting an inner formula, you have to hold that formula. Okay, so a knot takes an inner formula that it's negating. Hopefully this is all self-explanatory. And then, maybe I should separate these. Variables are formulas, really, by themselves. They're just a single variable. It's technically a formula. And they have names, that's all. They're just strings, P, Q, R, things like that, whatever you want. And yeah, they are their own variable name. So feel free to look at how I implement those things, but let's get started with evaluate now. These are the two functions that we'll talk about soon, but that's going to be the main work of this lab. Okay, first you need to implement evaluate for all these subclasses. All right, so let's go to test logic again to see what's going to happen. So you're going to evaluate a particular formula. You say evaluate, and you give it a variable to values mapping, so some map. And it's supposed to like try these particular variables in this particular formula. Okay, hopefully that's not too bad. And so we know how to make it, but how do we evaluate? Because that's what you're going to be implementing. You're going to implement here in logic.cpp, here's all the stuff that I've implemented, but here below is all the stuff that you'll be implementing. You need to implement all of these overridden evaluation methods. So like, for example, when you have an and, how in the world are you going to evaluate an and to true or false? And so that's the question. So you know how to build it up now. How do you evaluate it? Okay, so here's the trick. Every formula you can think of as a tree. And I think I say this here too. Yes. We'll just go back and forth. So every formula is a tree. And so the code that I showed you, it essentially is making this tree in blue here. P or Q and not R. It's or of first a var on the left-hand side, and then on the right-hand side, it's a big and that we've built up using on the left-hand side the variable q, on the right-hand side the not of a variable called r. Okay, so that is essentially what you get when you build up a formula. It's a tree. Okay, that's the key. It is just a tree. And so to evaluate, what you're going to do is do tree operations. You're going to make recursive calls to left and right, okay, to the left-hand side and the right-hand side to recursively evaluate. Because if you do that, if I can, I don't know, maybe I'll just copy all this because why not? If you do that, here's what happens. I'll make it small. So now I can write on it to my heart's content in a fourth color. So the idea is once you have this data structure that looks like this, you can package together in your, you say dot evaluate with your var to val map. You pass that along, which says, okay, I'm going to evaluate this particular Boolean expression with p set to true, q set to false, r set to false. And the way you do this is recursively, okay? So whenever you see an or, for example, what you can do is make a recursive call down the left-hand side, down the right-hand side, and that will give you back 2 Boolean values, right? So if you make the recursive call over here to this subtree, you get, well, whatever var p evaluates to, which is true, okay? And if you make a recursive call to this subtree, you're getting back whatever this whole thing and of q and not r is, and that is going to be itself recursively evaluated to, okay, var q is, well, that's false, var r, that is false, not of that is true, so and of this is false, this is true, well, it's still false, and so the entire subtree here evaluates to false, okay? I hope you see how that's working. And then the big thing is, the result of this whole thing is this true or this false. Because you've got an or, and then you're ORing together these two things. You just evaluated them, okay? So it is a recursive operation, all right? So that's enough writing. So you can read about this down here too. So to evaluate anything that's not a variable, you can recursively evaluate its children and combine their results. So if you're evaluating this or, for example, it has a left-hand side and a right-hand side. Here I call them x and y. This can be any formulas, and you know, because it's a formula, you can call evaluate on it. So to evaluate this or, you can first individually evaluate x and individually evaluate y to get something back, okay? And then you can combine them together using or, because that's what it means to or together two things, right? Hopefully that's slightly coming together for you. And then finally, your base cases for this recursion is when you hit a leaf. All the vars are always leaves, and the answer is, the way to evaluate a var to true or false is to use this map. So, okay, I see var q, I need to evaluate it to true or false. Well, I'll just look it up in the map, okay? The user has to give you those values. You can assume that they always do. So yeah, that's all you have to do. So you have to implement evaluate for all of these different formula subclasses, and hopefully with everything I've said, you can get started. So you need to use each piece of the and to determine if the whole thing is true or false. This is going to be a recursive function, okay? There, that's a method. It's a recursive method. Evaluate first LHS and RHS, okay? And so you're going to do essentially that for all these other ones. Var is special, that's the base case. Okay, so that's evaluation. Next is actually SAT solving. So now that we have formulas and we know how to evaluate them, we need to try a bunch of different mappings of variables to values and find all of them. Okay, so that's why there's a set of maps. The maps are the variable to value mappings. That's one particular solution, and then we want all of them, so we're putting them together into a set. Okay, so yeah, you're going to write SAT solve. And what SATSolve is going to do is it's going to call SATSolve helper, which actually does the real work. So I think how I want to explain this is to give you an example, probably in Racket, because what you're going to do is you're going to recursively try every possibility for all these different variables. So if you know that you have P and Q and R, you have to try P set to true, Q set to true. You have to essentially make a truth table. Try everything, right? All this stuff. So let me make an example for you in Racket that generates all the combinations. Of things. And that's essentially what you're going to be implementing. So I'm going to make a nice example for you. So let's pretend we have 5 variables, x, y, z, p, and q, and they can each take on one of 3 different values, a, b, and c. I think you can see how this is similar, where your lab is slightly easier. You only have to do true and false. That's the values that every variable can take. So I'm going to print all the possibilities of x, y, z, p, and q as a, b, and c, okay? So the way I'm going to do that is with a recursive function again. So I'm going to print all the possibilities, and I'm going to save I'm going to start out with a bunch of unchosen variables that I haven't picked values for, And then I'm going to slowly build up with each recursive call my chosen variables argument, which holds the choices that I've made. And this will make a lot more sense once I give an example. You know what? I've edited this slide so that we're going to try a smaller list of things. We're going to try to pick values for x, y, and z among a, b, and c. That's going to make it easier, I think. Oops, forgot to delete it there as well. So here's what we can do. Here's how this function is going to work, and the reason it's going to be recursive. We're going to start out having picked a bunch of things, or having not picked a bunch of things, having a bunch of things left to pick. X, y, and z need values. And then chosen vars starts out being empty because we haven't picked anything for it. And so the first call to this function, I'll just call it p, is going to be x, y, z, and then nothing. Okay, you can imagine these are strings as well, but I'm going to be lazy. Okay, so this is going to then call 3 different options because we need to take out an x and then try all the x possibilities. So this is going to need to call, okay, p of y, z, and we've made a choice. We have chosen that x should be a in this case. And in this case, we'll say p of, we still need to try y and z, and we've chosen for x to be b in this case. And in this case over here, we need to try y and z still, and we've chosen for x to be c. And so this is why it's recursive, because you're going to keep trying these options. So I'm going to skip these subtrees, and we'll focus on this one because it's going to get long. So this again has 3 options because it's going to find the y and try all the possibilities for the y. So it will make a recursive call 3 times to p. Okay, I still need to pick z. Let's say that we chose x as a because we have to keep it there. And then we also now chose y to be a. Okay, that's this one case. And then this middle case is, okay, we chose y to be b. So we're going to have to make a recursive call to try all the possibilities for z under the assumptions that we've chosen x being a and y being b. Okay, actually that's a stray mark there. And then finally, it'll make one last recursive call. Okay, try all the possibilities of for z under the assumptions that x is set to a and y is set to c. Okay, so again, forget about those. This again makes 3 recursive calls, and finally we get down to a base case because we now have nothing left to try. Okay, in this case, this first case, we're going to save all this information and then pick stuff for z. X is a, y is a, z is a, boop, boop, and boop. And then in the middle it's going to be, okay, try, well, there's nothing left to try, and I've made all these decisions so far. I've said that x is going to be a, y is going to be a, and z is going to be b. And then finally, I've got no variables left, and here's what I've decided so far. X is going to be a, y is going to be a, and z is going to be c. Boop, boop. Okay, so hopefully you can see where I'm going with this, because now this is a base case. This is a base case. This is a base case. There's nothing left to try. I've made all my choices. And I think you can see with enough recursion, like we're going to try all these possibilities, and we're going to range through all the possible different values between A, and C, and C way down over here. Okay, so hopefully that makes sense to you. And this is how I implement this. So I got my print possibilities, unchosen vars, chosen vars, start it down here. I've got everything unchosen, nothing chosen, and I call it. In the base case, we have chosen everything, so unchosen vars is empty. And here are some things that you can do to lists that I'm going to be using. You can check if something's empty, first of all. The empty list is empty, everything else isn't. Then the rest of things is, let's pretend that L is 1, 2, and 3. You can get the first thing of the list, that's the 1. You can get the rest of the list, that's the entire list, 2, 3. And then you can build up bigger lists with cons. That makes the list 0, 1, 2, 3. And so now hopefully you can read the rest of this. So in the recursive case, we get out the first variable that we want to pick from, we take it out of unchosen vars, and then we extract it from unchosen vars to get the rest of them, everything but the first one, using rest. And then we just call our function 3 times recursively with the rest of the things that we still need to pick from, and we'll try all the possibilities for the variable. Either it'll be A, or B, or C. Okay, So yeah, hopefully that makes some sense. And here is it running, like, okay, here's all the possibilities. And you can see that it's going to make 3 to the 3, right? 27 possibilities. And it'll all work out. So this is how it chooses, and this is exactly what you're going to do in the lab, okay? One thing that I've made in the lab is a helper function so that the user doesn't have to worry about like setting this to empty. Instead, you could like say, okay, just print possibilities, or print possibilities pretty, just give all the variables you want to try stuff for. And then this function will automatically put in the correct initial values to this fancier function that does the real work. Okay, that's the idea. So I'm going to give you this file. Please study it, because you're essentially going to implement this. And I've implemented, or I've not implemented, but I've written a ton of comments in logic.cpp. So this is what you're going to do. You're going to call the satsolve method on a formula, and this will call satsolve helper to do it all right. And here is satsolve helper. This is essentially what you're going to be implementing with all this. Okay? So you're going to translate it there. If I could get back to it. Where did I go? There it is. Okay. So satsolve helper, it's going to take a formula. It's going to take a bunch of variables that you have not chosen anything for yet. And then it's going to take all your choices. So these are all familiar parameters now. So these are all the choices you've made so far for variables. It's represented as a map in C++. Okay? And then finally, one last parameter that we don't need in Racket, because in Racket I just printed things. We want to save all the satisfying solutions. So every time we come up with a choice that makes the formula true, we want to save that set of choices for variables into a set. Okay, so we have a set of maps for that reason. So then the base case, you add your current choices for vars to the satisfying solutions if you need to. Okay? And it looks like when I saved this, it did some weird stuff, and I'm sorry about that. I'll make it prettier again before I send it off to you. But yeah, you got a base case and a recursive case. If you just follow all these steps, it should all work out. But yeah, this is what you're going to do. You're going to try all the possibilities of whatever the variables could be for a formula f, and the way to get all the variables that are inside a formula is to use this method here, extract var names, which I've implemented for you. Okay, so I think that's all I want to tell you. Please yell at me if you have questions. That is your lab. So you're going to be doing two things. You will implement only stuff in logic.cpp. You're going to implement the evaluation methods for formulas, and you're going to implement the sat solving stuff for formulas. Okay, so essentially you're going to translate this code into C++. Okay, so give it a try. Yell at me if you have any questions. This is a 2-week lab, so you have a lot of time to do it. Yeah, that's all I want to say there. Turn it in as usual. You're just turning in logic.cpp. The satsolve tests are worth a lot more, obviously. They're harder. And yeah, something that I do want to tell you is you don't have to write more than like 30 lines, 50 lines at most, to get this lab 100%. But you have to think very hard about each line, as I think I've demonstrated. Okay, so good luck. Yell at me if you have any questions, and I will see you next week.